All right, folks. Well, welcome back. We are done with our discussion of conversions, and so please make sure you feel comfortable with the simple conversions at least. The more complex ones, the ones where we apply the conversions to doing problems with algebra, you'll get more chances to do that later on. But for our class here and for what we need it for, please make sure you can do the simple conversions, the length conversions, the time the length and time conversions. Don't worry about the masses and any of those other conversions. We need to be able to deal with lengths and we need to be able with time. Okay. All right. So with that said, after a fairly long delay in discussing our kinematics, okay, we're back at doing kinematics again. And what we need to be able to do here, and just as a quick review, we need to be able to obtain information about how an object moves. Okay, and so far, we've been talking about an object moving only in one dimension. And for our class here and for our purposes, we will continue only to talk about an object moving in one dimension. But we need to be able to describe the object's motion in terms of the distance that it covers, in terms of its speed and direction. So when you have speed and direction together, you have the velocity, and also in terms of its time, the total motion time it takes to undergo the motion, and also if it changes its speed, thus does it accelerate. So those four factors we need to be able to use in order to complete our description of a moving object. And that essentially is kinematics, folks. That essentially is kinematics. And so to obtain the velocity, we can measure the velocity. We can measure the rate at which an object covers a distance over a given time interval, and we call that the velocity. Okay, and then we were able to describe then that the change in that velocity over a given time interval, and we were able to describe that as acceleration. So we came up with two ways that we could determine the velocity and the acceleration. But we were also able to obtain that information from a graph. We were able to graph position versus time. Position versus time, we collect certain data points at the time that an object reaches a certain position, and we were able to graph that. And from the slope of that line, we were able to obtain position. Okay, slope of that line, we were able to obtain velocity. Okay, so the velocity then is obtained from the slope of a position time graph. The position time graphs gives us the exact position. We can locate the position at a certain time interval, whether it's from the data set or if we have to extrapolate or interpolate the data from the graph. We can obtain information about the position of an object and how far it moved over a given time interval. And then from that information, we can get velocity. But from a position time graph, we can obtain the positions and get the displacement of an object. So what we did was we talked about the velocity time graph. We talked about how the slope of a velocity time graph gives us acceleration. And the velocity time graph plots for us the velocity and the instantaneous velocity of an object at different time intervals. And so we were able to use that to get the acceleration as well, because the slope of velocity time graph gives us acceleration. However, the information that we do not and we cannot obtain from a velocity time graph is information about position and displacement. Okay? And so I kept on reminding you that we cannot get that. Okay? With the exception of with one exception, and that's what we're going to talk about today. Okay, all right. So what we have in front of us now is a velocity time graph. Okay, so velocity time graph. Remember, we have velocity plotted along the y and time plotted along the x. Okay? And so we have here 2 points. Let's go ahead and consider this here. We have v initial here, and then we'll just call this point right here v final. So this is v initial. That's v initial. This is going to represent v final. And so we said then if we needed to find the acceleration, we can find the 2 points here, get the time interval here at t initial, and then time interval here at final. Okay, so t final. Get those two times, get those two velocities, get the difference in those two, and then we get the acceleration. Okay, and so we can obtain the information here if we needed to. Now, the question then is, let's go ahead and take a look at this really quickly then. If we had the acceleration, if we know what the slope is, and we had the initial velocity, we know what that is, could we get v final from this graph here? Okay? And that's what I want to do real quick here. I want to do a quick analysis of the graph here, and let's see what we can get. So let's see then if we can obtain this from the graph. Okay. All right. So from this graph here, what we see then is if we go up here, we see then that this point here, this distance here represents v initial. Okay. This distance here, as we see, this distance here represents then the velocity, okay, that we will need to get to this final velocity. So a times t. Let's go ahead and do this really quickly. Okay. So let's do a unit analysis of acceleration times time at this point. Okay. So acceleration times time, the units for acceleration is going to be meters per second squared, okay? And here we're multiplying it by time, okay? Meters per second squared times seconds. So essentially this distance here is a velocity, okay? So we have a velocity there, okay? That represents the velocity that is obtained as the object accelerates. Okay? So as the object accelerates, okay, it's the velocity that it obtains, okay? And so if you take a look at this, if we go ahead and in order to get v final, so in order to get v, to get to this point here, we need to take the initial velocity. Okay, so in order to get v final, okay, we need to take the initial velocity there and add it to this change here, which represents a times t, and that will give us v final. And that was the equation, folks. So to get this final velocity here, to get this this final velocity here from the graph, okay, we need to get then this distance here, v initial, and we're going to add it to this velocity here, the velocity that is obtained as you go from v initial to v final. Okay, and again, doing the quick analysis here, folks, a times t is going to give you acceleration times time. Is going to give you velocity. Okay, and so you can add that together, then you obtain this formula here, which we see then, and that we've been using up until this point. Okay, so basically what we did is, and we were able to obtain this equation here from rearranging actually the equation for acceleration. We saw then we were able to obtain the equation for acceleration as from the graph here, and we got that this particular equation, the formula, expanded it out. And then again, rearranging the equation, we get this one. But again, we can get this graphically. We obtain this same equation here from the graph here. And then if you notice here, this graph here is in the form of the point slope. It'll be arranged as here, AT point slope formula, with this being the y-intercept. There it is. Okay, and this being the slope, the acceleration being the slope, and there that is. And then we have time and final velocity. Okay. All right, very good. So so we can obtain this information graphically. We can get this information and we can obtain it graphically as well as getting the formula. Okay. All right. So the point. So with that said, then what I hinted at here was that if we have a velocity time graph, can we obtain information about displacement? Are we able to obtain information about displacement? Okay. Well, let's consider this velocity time graph that we have right here. Let's consider this velocity time graph right here. Okay, so we have velocity and time. Okay. I want to quickly do a dimensional analysis, an analysis again of what we have here. Okay, so here we have an object moving at constant velocity. Okay, so the acceleration here is going to be 0 meters per second squared. Okay, so we have an object moving at constant velocity of 20 meters per second. Okay, so we have a velocity. So remember, constant velocity means then that the velocity does not change, but it doesn't mean that it's 0. The acceleration is 0, but the velocity is constant. Okay, so constant zero acceleration means then velocity is constant. Here we have then a velocity of 20 meters per second. Okay, all right. And so if let's go ahead and consider then the 4-second time interval here. Okay, so the time then from 0 to 4, it can be 4 seconds. Okay, all right. So we have a velocity of 20 meters per second, time then of 4 seconds here. And so what I would like us to do is let's take the product. Let's multiply those two. So let's just really quickly multiply those two together. Okay, so we're going to multiply those two. And so let's go ahead and plug it in. And let's do this really quickly. So it will be 20 meters per second times 4 seconds. Okay, so we plug that in. The number then is 80. That's pretty much simple enough. However, do the unit analysis here. So it's meters per second divided by seconds, and we get meters. Meters is a unit of length, folks. And so what we have done here is by multiplying the velocity times the time, this is constant velocity, velocity times the time, we have the distance that it covers. So if an object is moving, and again, this is constant acceleration, if the object is moving, and it's not accelerating, I'm sorry, if an object is moving at a certain rate, and we can time it, okay, in that given time interval, from that we should be able to obtain how far it moves. And so from a velocity time graph, we can obtain displacement, okay, by just taking a velocity and multiplying it by its time. Okay. Now, if you notice here, what we've done then is, if you look at, and I've shaded the square for you here, what we've done then is that we have taken the length and the height, the width of this particular rectangle that we can form. So if you take a look at this rectangle here that forms here, okay, and so if you take the length and the width here, you have found the displacement. So the area underneath the area. So if you take the area there, the area underneath that that rectangle, which is length times width, is going to give you the displacement. Okay. So the area underneath a velocity time graph, and that's what we calculated here, the area underneath the velocity time graph will give you the displacement, and that's the equation I give you there. So what we can do then is, from a velocity time graph, we can get the information, we can obtain the displacement if we find the area underneath the graph. If we find the area underneath the graph, we can find the total displacement, and that's what we have right here. And so let's make sure you understand this. So calculating for the area underneath the velocity time graph, we will get the displacement. So we can't get the displacement directly from a velocity time graph, but we can calculate for it. We can calculate for it by simply going ahead and calculating for the area. Okay. All right. So with that said, then that is. Oh, sorry. Oh. So let's go ahead then and let's try this. Let's take a look at this problem here. Okay, so we have then the a velocity time graph. Okay, and we have an object moving at constant velocity. Constant velocity means the acceleration then here again it's going to be 0. Okay, so the acceleration here is 0. The velocity is constant, and so the velocity then, if you take a look at this, this is about 75 meters per second. Okay, so velocity is 75 meters per second. Okay, and they want us to find then the displacement at 1 second. So at 1 second here. So let's go ahead and draw that line. And then at 2 seconds. Okay. All right, so displacement then is the area underneath the velocity time graph. So the first time interval here is going to be 1 second. Okay, so if we can find the area underneath this particular graph here, okay, then we can find the displacement. So let's go ahead and do that first. Okay, so displacement 1 is going to be equal to, and here then this is going to be length times width. So the this first the length here, the width here is going to be 1 second. The length here is going to be 75 meters per second. Okay, so this is going to be area. It's going to be length times width, okay, which is going to be then 1 second times 75 meters per second. And then we end up with 75 meters. I think it's pretty straightforward, folks. Not that difficult here. Okay. And so with that said, then, if you do the unit analysis here as well, seconds cancels out, and we get 75 meters. Okay. All right. Let's go ahead and let's do the second. Let's do the second displacement. Okay. Now we're dealing with. Let me go ahead and fix this really quickly. Okay. Right. Now we are dealing with a larger rectangle. Let's say then we are. They want us to find then the total distance traveled, okay, for 2 seconds. Okay? All right. So now the time is the length here that we have is not 1 second. Okay, but we're dealing with the total time now of 2 seconds. And so the length here will be 2 seconds. The width now will still be 75 meters per second. This side here will still be 75. Okay, but this side now is going to be 2. And so let's go ahead and find the area underneath this larger triangle right here. I'm sorry, rectangle here. And so we have then 2 seconds times 75 meters per second. Okay, and if we plug that in, then we would get that 150 meters. 150 meters, sorry, not 150 meters per second. Okay, 150 meters, and that's it. Okay. All right. So finding the area underneath a so again finding. Let me do this. Okay, so finding the area underneath a velocity time graph. So you plot the velocity versus time of an object. You find the area underneath that particular graph. You get then the you obtain then the displacement. Okay, so that I think is pretty straightforward. Now it's pretty straightforward for an object. So we've been working with an object here that has, and the key here then that is not accelerating. Okay, there is no acceleration and it's moving at a constant velocity. What happens if you have an acceleration? What happens if the acceleration is not 0, but but you have a constant acceleration that is non-zero? Okay, well, this becomes it doesn't become that much more difficult, because it's still true that if we can plot the area underneath a velocity time graph, we can find the area underneath the velocity time graph, we can obtain the displacement. Okay, so you can imagine this here. Okay, if you are looking at this, so here we have velocity time. Okay, this time though we have a slope. So the slope here represents the acceleration. So the acceleration here is not equal to 0, folks. The acceleration here is not equal to 0. But if we take a look at this, then here is the velocity. Okay, if you take a look at what we have here, then is the area underneath this curve here. The area underneath this shape here is not a square, but it's a rectangle. So how then would we obtain the area underneath this curve here? Well, the area underneath this curve here then is going to be 1/2 base times height. And this will still hold true, folks. And let's do the unit analysis here. The base here is going to be time again. So, and the height here is going to be velocity. Okay. So with that said, then if we plug it in and do the unit analysis, then the area is going to be equal to 1/2 the base, which is going to be units of seconds. Okay. The height, which is going to be units of meters per second. That cancels out. And what you'll notice here is that though that when we do unit analysis here, this is not a unit, so we don't have to worry about it. But the unit that we end up with is still meters. And so the area underneath a velocity time graph, regardless of whether you have constant velocity in which the acceleration is 0, or you have a change in velocity in which the acceleration is not 0, you can still find the displacement as long as you can recognize what the shape is going to be. So for constant velocity, the shape is going to be a rectangle or a square. Okay? For a change in velocity, the shape is going to be a triangle. And so you can approximate that displacement by calculating for the area underneath that triangle, and then you have your displacement. Okay. All right. So with that said, then let's take a look at an example. Let's take a look at a couple of examples. Okay. So we have 3 plots here. I want you to 3 graphs here. I want you to take about the remaining time here, and I want you to work out I want you to find the displacements for these 3 objects here. So you have 3 objects with the velocity time graph plotted for these 3. I would like you to calculate for the velocity time, for the displacement for each one of these. I'll start out and I'll work out one of these for you, and we'll work out the remaining 2 on Monday. But let's go ahead, take about 5 minutes to work through this one. And then I will work out the first one, the first 2 for you, and then we'll leave the last one for Monday. Okay, so go ahead, take 5 minutes, work through these problems here, and then let's take a look at them. Okay. All right, let's go ahead then and let's take a look at the first one. Okay, I think this is pretty straightforward. Let's go ahead and let's work this one out together. Okay, We see then, first of all, let's go ahead and recognize something here, that the acceleration here is 0. Here we have 0 acceleration because the velocity is constant, and the velocity here is 4 meters per second. Okay, so again, here this is, and so because this acceleration is 0, if we find the area underneath the square here, then we can find the displacement. Okay, so let's go ahead then. If you take a look at here, the length then, and I'm arbitrarily choosing the x-axis length here, it's going to be 15 seconds. The width here then is going to be 4 meters per second. Okay, and so the area underneath the curve here, which is going to be length area, area of the rectangle, will represent the displacement. Okay, so the displacement then is going to be equal to the area. Let's plug in our values here. The length then is going to be 15 seconds. Okay, and the width then is going to be the velocity, which is 4 meters per second. Yeah, we plug that in then, and we get our displacement as being 60. Okay, 60 meters. Pretty straightforward, pretty simple stuff. I don't think it's that difficult. Okay. All right, so I've run out of time right here. So what I'll do then is we'll work out the remaining two, and the remaining two represents, if you recall, those have changing velocity. Velocity is changing, and so we have to deal with an acceleration there. Okay, but the area, again, to find the displacement, we're just going to find the area underneath that curve. The curve just happens to be a triangle, so we can draw the triangle. Calculate for the area underneath that triangle, and that will approximate for us the displacement. Okay, so hold on to this paper here, folks. Make sure you submit it. Hold on to the paper, and then on Monday we'll work out the remaining two problems for this particular the 2 graphs for this particular problem here. Okay, all right. So very good. Have a good weekend, folks, and then I will see you on Monday. Okay.